All right, AP Physics. Mr. Jewell here. I am obviously not here in class today, but I thought I would go ahead and record a little bit of a video for you just to kind of go over some things that we talked about on Wednesday afternoon with the students that could make it. So if you were one of those students, then you've seen this before, and if you weren't, then this might be new to you. It's just kind of a recap of what we talked about last class, and want to work through a couple of the homework problems with you just to help you out and getting you started on this. So it came up that one thing that was kind of lacking were procedures for solving these sorts of problems with things moving on inclines and whatnot. So this is the list of sort of steps that we came up with on Wednesday afternoon. First one was to draw a free body diagram. So in your homework, I'm expecting to see lots of these free body diagrams. That's a diagram that shows all of the forces acting on the object. After you've drawn your free body diagram, you're going to want to break the weight, or mg, into x and y components. And we are going to go ahead and define the x component as being parallel to the slope and the y component as being perpendicular to the slope. And we're going to define the y as being perpendicular to the slope. So we're defining our positive y direction in here, our negative y direction here, our positive x down here, and our negative x in that direction there. After we've done that and we've broken our weight, this mg down here, into its components, which we could think of as drawing a line, drawing a little parallelogram like so. So if we do this, let's see if we can make this work. End arrow, we want to have this solid. We would have an x component. Let's see if we zoom in. An x component here and a y component here. And we previously, in the last lecture, sort of showed why this works. But the x component is mg sine theta, and the y component is mg cosine theta. The reason I'm asking you to draw another free body diagram is this looks a little wonky. This looks like there are 5 forces acting on the block, when in fact there are only 4. So we're going to redraw it without the mg acting down and only draw in the components, like we have in the second free body diagram here. Then we are going to sum the forces in the x acting on the block and set that equal to ma. Remember that the a is equal to 0 if the block is not moving, or if it's moving at a constant velocity. In other words, if it's not accelerating. So if acceleration equals 0, it's at equilibrium, and this whole term on the right hand side of the sum of the forces equal ma becomes 0. We're going to do that in the x direction and the y direction. So in the x direction, this direction, we have mg sine theta and we have friction. So in the positive x direction, we have mg sine theta. In the negative x direction, we have friction. Well, I've written down here, let's see if I can zoom in on this. This whole term here is friction. We know that friction is equal to mu times force normal. Remember, friction equals fun. See? Ha 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 ha. Is mu force normal. We also know that force normal, since there's no acceleration into or out of this plane on the y direction, is equal to mg cosine theta. So I can substitute this into in there and friction. So friction then becomes mu times mg cosine theta, which is the term I have here. So when we sum the forces in the x, we have mg sine theta acting in the positive x direction and friction acting in the negative x direction, which gives us these things. Now usually this is enough to solve for whatever it is we need to solve for. You'll notice here that since we have mass in all of our terms, it's going to cancel out. If we divided everything by mass, that would all cancel out. So most of the problems here are not going to give you a mass because you don't need it, because they all cancel out in this form of the equation. In the y direction, I talked about it just a second ago, but in the y direction, when we sum the forces, we get the normal force acting to the positive y direction, and we get mg cosine theta acting in the negative y direction. So we have n, the normal force, minus mg cosine theta equals 0, which means that n equals mg cosine theta, and that's what we used before. Okay? Most of the problems you're dealing with in the homework are going to deal with the x direction, in other words, sliding down the ramp. So let's take a look at a couple of problems here and see if we can clear this up. If you want to jot any of this down, just pause it and write that down now. So we'll start with problem 37 here. This says a force of 48 newtons is required to start a 5 kilogram box moving across a horizontal concrete floor. So, I am having a hard time drawing a straight line here. Let's see, horizontal concrete floor. Here's the box, 5 kilograms. What is the coefficient of static friction between the box and the floor? Well, let's start with a free body diagram. In this case, we have an easier time because we're not on an incline. It's just a horizontal floor despite what my wavy line looks like. So we're only going to draw one free body diagram. We are going to have mg acting down. We're going to have our normal force acting up. We're going to have friction acting to the left, and we're going to have our pulling force, which is equal to 48 newtons, acting to the right. So the first thing they ask us to do is the static friction, which means the box is not moving. Our y is not going to be important, so our sum of the forces in the y direction are 0 and pretty much irrelevant to the problem because we're looking for friction, we're looking for stuff in the y direction, or the x direction. So sum of the forces in the x equals ma. In this case, we're not moving, so again, we have a static situation. Sum of the forces in the x equals 0. The positive x direction, I have 48 minus friction equals 0. Let's expand on our definition of friction. We know that friction is equal to mu times force normal. In this case, we're looking for the static friction, so we're going to use mu sub s. And furthermore, I can replace my force normal with mg, actually going back here, because this is not moving into or alpha the floor, there must be an equilibrium and those two forces must be equal. So I can write 48 times mu sub s times mg. I know what mg is. M is the mass, which is 5 kilograms. G is gravity, which is 9.8 meters per second squared. And now I can solve this equation. So I'm going to subtract 48 from both sides and divide by negative, which will mean that will be mu sub s equals 5 times that, which is 49, equals 48. So the static friction, now you have to divide both sides by 49. Mu sub s equals 49 divided by, other way around, 48 divided by 49. Which, let me grab a calculator here, equals 0.98. Which means that you have to pull with 98% of the downward force, or 98% of the weight of this box, to get it to move before you break static friction. Alright, so we're going to record that off to the side here. We're going to say mu sub s equals 0.98. I'm going to erase this so that we can do it again. What changes now for part B. Part B says 48 Newton force continues. The box accelerates now at 0.7 meters per second squared. What's the coefficient of friction? So now the left-hand side of our equation actually is going to remain completely the same. None of this stuff on the left-hand side changes, so maybe I won't erase the whole thing. Maybe I'll just erase like the bottom part here. What's going to change is that now our system's accelerating, so the right-hand side changes. Now, when we do F equals ma, we have an a. Our mass is going to be 5, and our a is going to be 0.7, which makes the left-hand or the right-hand side of the equation 5 times 0.7, which is 3.5. 3.5. The other thing that changes is instead of finding static friction, we're now finding kinetic friction, so that becomes mu sub k. Okay, so to go through the same procedures, 48 minus mu sub k times 5 times 9.8 equals 3.5. So 48 minus mu sub k, this we just said equaled 49. So we have 3.5. We need to subtract 48 from that, which gives me negative 44.5, and I divide that by negative 49. And now I get mu sub k equal to 0.91, which makes sense. It needs to be lower than my static friction. So my static friction is 0.98. That means I have to pull with 98% of the weight to get it started. In order to keep it accelerating, accelerating at this particular rate, I need to continue to pull with 0.91 or 91%. Okay? Cool. Hey, look, I did it yesterday too. It still worked.